Hi there, welcome to the second part of Monday's lecture for Physics 212. Thank you very much for helping me by taking part in this new media while I'm here at AAPT in Florida. We've been working on Newton's universal law of gravitation, and I think what we'll do now is we'll work on another sample problem. Here you see what we've been doing thus far is the only new topic in this chapter is that the force between two gravitational objects is given by Newton's law of universal gravitation, you see up here in the upper right. And all problems that we're going to work on in this chapter can be solved using just that one equation. And often we're going to integrate that to find work. So let's try doing this sample problem. Okay, wait. Quick note, I just checked my math, and make sure that you do G and M and everything else in this problem to the correct number of sig figs, or else mastering physics gets kind of cranky. So remember that the mass of the sun isn't 2 times 10 to the 30, it's something like 1.99. Okay, so I promised I'd do a sample problem, something that people asked for from the homework. So this is problem 13.58 from our textbook. Okay, so in this particular problem, we've got 3 stars, or 3 suns, each with the mass of our sun, forming an equilateral triangle with sides given, and this triangle has to rotate because otherwise the stars would crash in together towards the center. The question is, what is the period of rotation of these suns? Remember, just like the planets in the solar system orbit the center of mass of our solar system, as opposed to the sun, these 3 suns are each going to orbit around their center of mass. So, as in all physics problems, the first thing we do when we're trying to solve this is draw a picture. And in our picture, we're going to have 3 suns, each forming a triangle. Now, the solar system has only 1 sun, but most stellar systems actually have 2 or more suns. So this is by no means an unlikely scenario, although the equilateral triangle probably is. In our picture, we should somehow show that all the suns are orbiting in a circle. We were given this distance right here. Let's call this distance L. And we're given that each of the suns has a mass equal to our sun's mass, which happens to be around 2 times 10 to the 30 kilograms. And they're all orbiting the center of mass of the system. Okay. Once we've drawn our picture, the next thing we're going to do is draw a free body diagram. Now there's 3 bodies in this problem, so we might need to draw 3 bodies in the long run, but let's just try working on 1 and see if that's enough. So let's draw a free body diagram on the top star. So here's the object, and that object is experiencing a force from each of the suns below it. So that lower left sun is going to pull it in this direction, and the lower right sun is going to pull it in this direction. Gravity is always an attractive force. And so that upper sun is being attracted to the 2 lower suns. Every free body diagram should, of course, have a coordinate system. Let's label our forces. Each one of these is going to be a force due to gravity. And we're not done there. We, of course, always have to draw in an F net. And in this case, because there's symmetry in this problem, both suns are being pulled equally in this direction. And we've done problems like this where we had a sled being pulled by two ropes and angles like this. Nothing different than when we're dealing with gravity. Our F net is going to end up pointing straight down like that. Okay, so we've drawn our picture, we've drawn a free body diagram. Let's do the next step, which is let's try to derive some equations. And see if we can figure out how to go about solving this problem. Okay, so as we look at our free body diagrams up above, we're of course going to break everything into I hat and j hat components. In the I hat direction, we've got a g m over r squared. We have to be a little bit careful. Let's go back up and look at our drawing. The r we want is not the length given, but rather this is the r we want. The r, let's make sure I get this right. The r squared here is not the radius of the circle, but rather this r squared is the distance between the two suns, which is the L. So this r squared is actually not going to be an r, it's going to be L. And we have to take a quick look at the component. We're going to need to look at this angle right here, and the x component is going to be this bit right there. So really, we also need to have a sine there, sine theta button there. In the I hat direction, there are two suns pulling with this magnitude, but they're pulling in opposite directions. So when we do the sum of the forces in the x direction or the I hat direction, they're going to add up to 0. In the j direction, however, they're going to both pull downward. And, well, that 2 doesn't show up there yet, but it will. We end up getting something that looks like this. Now, all these suns are orbiting at a constant speed, and they're moving in a circle, so that means that the sum of the forces in the j hat direction at this instant have to add up to mv squared over, in this case it's not L, but it is indeed R, because they're going in a circle. That distance must be the radius of the circle that's formed as the suns go around. Okay, so we've derived some equations. But we started to derive some equations by breaking everything up into components. Let's see if we can solve for this. Looking in the j hat direction, because the I hat direction is not going to matter in this case, we get that 2gm m squared, because both m's are going to be equal. Let's just squish them together down to 1m right now, over L squared cosine theta is going to equal mv squared over r, where again that m is the same m as we were dealing with the other suns. Some of those m's are going to cancel out. We were asked to find the period of revolution, period of orbit. So if we look at this problem, that period is going to hide in the velocity. And the speed always has a time in it. Again, each sun is going around in a circle. Its speed is going to be the distance it travels every period. So every 2 pi r, it's going to take a period tau amount of time. And let's try, oh, and the other thing, notice we have an L on one side and an R on the other side. Let's see if we can figure out how R and L are related by going back up to our picture. We're going to have to do some triangle drawing here. Let's try looking at a triangle like that. Notice that this distance up here is not going to equal this distance down here. So let's try bisecting the triangle like that, which this distance right here is going to be r as well. And this distance down here is going to be L over 2. In our drawing below, this theta here is going to be equal to, let's make sure we get this right, the theta up here in the drawing is going to equal the theta down in our free body diagram. We know the adjacent length, well, that's what we know the adjacent length. We're trying to find the hypotenuse length. So we know that cosine of theta is adjacent over hypotenuse. And if we were going to put r in terms of L, then r is going to equal L over 2 cosine theta. Let's try to throw that in down below. When we solve for it next, that was r is going to equal L over 2 cosine theta. So let's do some more plugging and chugging. 2gm over L squared. Cosine theta is going to equal 4 pi squared r squared over period squared all over r. These r's are going to cancel out. Solving for period, we're therefore going to get that the period is going to equal 4 pi squared. That r is going to turn into an L over 2 cosine theta. Okay. And that L squared is going to pop up here to make that an L cubed. And on the bottom, we're going to end up with a 2gm with another cosine theta. Okay, let's make that just a little bit prettier. Oh, and of course, the tau was originally squared, so let's square root this side. And we're going to get 4 pi squared L cubed all over all over 4 cosine squared theta gm the square root of. And if I've done my math correctly in non-SI units, this should all be around 10 years. Plug and chug this, see if you get it. Okay, thank you very much for taking part in this online Physics 212 lecture. I'm going to throw a third part up, a little bit from Johnny Lee, and show you a little bit what we've been doing here at AAPT. Meanwhile, I look forward to seeing everyone tomorrow morning and tomorrow afternoon. Bye-bye.